So today we're going to be doing our 6-8 notes, which are going to be nth roots. And just so you all know, you have your Module 6 test. It'll be open notes on the 27th. Okay, it'll be a computer test. We'll do it in class, but I just want to keep reminding you as the date comes up. So we'll have finished all of Module 6 by then. We'll do a review and all that. Alright, so let's talk a little bit about radicals. So, yes.
This is the 22nd, right?
No, the 27th.
Oh, that makes so much more sense. I was so confused. Okay, thank you.
You're welcome. So, if you see a radical, we have some important parts to know about the radical. We have the radicand, which is everything inside the radical. And then we have the index, which is the number that sits between that little V shape on the radical. And that indicates what kind of root we're taking. Now, you're most used to seeing a square root. A square root has an implied index of 2, okay? So any other index, like 3, 4, 5, that tells you what kind of root you're taking. So if there's no index, you assume it's 2. If there's anything else, you need a pencil. They're right behind you, a whole cup of them. Oh, there's not one in there? Here you go. So a principal root is basically the positive real numbered root of an even index radical. Unless otherwise stated, principal roots are implied when dealing with even index radicals. So while there's multiple different roots of 16, we always talk about the positive 2. Okay, so you assume the simplest form unless otherwise stated. Now, I gave you some charts of perfect squares and perfect cubes and perfect fourths, so you can use this to your advantage as you go through the lesson and the homework. Okay, these are going to help you at least be able to identify the first few, so you can use them in your practice. Okay. So let's go ahead and zoom in and just do some basic problems here. So this is just a regular old square root. So anybody know what the square root of 121 is?
11.
Good, and that's a perfect square. And it's a perfect square because this breaks up into 11 and 11. So anything that gets paired up gets to leave as 1 in a radical. Okay, and there's nothing left over, so nothing stays inside the radical here. Now we're looking at a third root. So with a third root, you want to look for a pair of 3. So I know that 343 breaks up into 49 and 7. I'm circling the 7 because 7 is a prime number and I can't break it down anymore. What can I break up the 49 into?
7.
Good, 7 and 7. Now, like I said, you want a group of 3 because that's your index.
So that would be a perfect third.
It would be a perfect cube root. Very good. It's a perfect cube root of 7. Make sense? No leftovers on that one? All right. So, what? So this one here, you could sit here and break down the whole thing. It gets a little much. So I'll talk about both ways to do it. The other way you can do it, if you see something really big and you see it's a fourth root or third root, this is the other procedure you can use. You can look at this table of fourth roots. And you can start dividing your number by these. So obviously your number's not going to be evenly divisible by this because it's almost the same size. Now we would try dividing it by this number here. And if it goes in evenly, we know that there's going to be 4 6s in it, right? So basically, I know that this breaks into 2 times, whatever it was, I don't remember now. I have it written down. There we go. 1,296. And you could go ahead and break down the 1,296. Okay, the 2 gets circled because it's prime. Now this I know will break up into 36 times 36. And then each of these are going to break up into 6 and 6. And 6 is not a prime number, but do we have a group of 4 6s here?
Yeah.
You can take that out now. Now you could keep going and do 2, 3, 2, 3, 2, 3, and then take out the 2's and take out the 3's and then multiply them. But in the end, it's going to give you 6. So the 6 gets to leave the radical here. Okay? So we got a 6 that leaves, and then what has to stay behind inside the radical? the 2 that didn't get paired up with anything, okay? So you can also split fraction radicals like this, and you're going to see why that's helpful here. If you look at your chart, these are both perfect 4th roots, right? What is, yes?
For C, does that say 64?
No, it's like 6, and then it's like the index is 4. It's like that.
Wait, so do you put it below the 6?
On which one?
On C.
Oh, so your index is going to go in that little V shape in the radical. So see how it's written right here? You see how the index is, that's how you want it to look?
I see how the 6 is not really in the little V shape, it's kind of outside.
Yeah, so the 6 is like a number on the outside.
Got it.
Okay. Yeah, it's confusing sometimes to write it in the small space and make it look, you know, the way you want it to. I always put my number a little higher so you can kind of tell that it's not the same. So what is the perfect 4th root of 81 according to your chart?
3.
Good. And the perfect 4th root of 16?
2.
Good. So it's 3 halves. So that one you just use the chart. Alright, so let's talk about negatives. So we all know that when you try to take a square root of a negative, you get an imaginary number, right?
Correct.
However, you can take odd roots of negative numbers, okay? So if your index is odd, this is not going to be imaginary. I'm going to show you why. And then once I show you why, I'm going to show you the easier way to deal with this. So, I know that 125 can break up into -5 and +25, right? -5 is prime, so I'm going to circle it or box it, however you want to do it.
Oh, then you could do -5 and -5.
Exactly. Now, yes, 25 breaks up into +5 and +5, but why would we want to pick -5 and -5?
Because you want all 3 to like be the same, so you don't have to do some weird radical thing.
Exactly.
Yeah.
Once you can get a pair of 3, since it's a 3rd root, these get to leave the radical as 1, right? Because they're a group of 3. So the answer here is actually -5. That's actually a perfect cube root. So that's the reasoning behind why that works. Now, when you're dealing with this, I don't want you to go through this game of figuring out what's negative, what's positive, because if you're dealing with something like in the 2000s, it's going to get really, really dicey to kind of start doing that. So here's what I want you to do. I want you to rewrite it as the product of -1 times that radical, but make it positive on the inside. And that's going to give you the same answer, because this is going to come out to be 5. What's 5 times -1?
Oh.
-5.
There we go. Yeah. So that's another way to do it. I just want to explain that to you guys. That's easier than the alternative. Okay. So let's go ahead and talk about the even, odd mnemonic device. I can never say that word. We're just going to go with it. So the reason that this is required is, say you take an even root of this right here. Well, first, you're typically going to simplify what's on the inside, right? What's -6? My voice. What's -6 to the 2nd power?
36.
Mm-hmm. What's the square root of -6? Or +6, sorry.
36.
Yeah, I meant to say, what is the square root of 36? The answer is 6, okay?
Oh, there we go. Yeah.
So, see how the answer you get is not what you started with inside the radical?
Yeah.
That's because of this even root index rule. So we're going to talk about how we deal with that. So when variables are involved, if you are taking an even root of an even power and end up with an odd power answer, place an absolute value around the odd power variable answer. So we're going to practice that. It sounds complicated, but it's honestly not. It's just a way of dealing with a problem. So if you take an odd root, or I'm sorry, if you take an even root and you get an odd answer, you can't have a negative under an even root. So this is like a workaround to make sure that doesn't happen. Because we know absolute values make numbers what? positive. Alright, so let's go ahead and try it with some radicals dealing with variables. So actually taking radicals of variables is actually very easy. What is the index of this radical here?
2.
Good, it's an implied 2, right? So what you're going to do with that index, you're going to divide these powers by that index, okay? So what is 4 divided by 2?
2.
Are there any remainders?
No.
No. What is 18 divided by 2?
9.
9. So see how there were no remainders in either case? They both evenly divided by the index. So nothing gets left inside the radical here. Now, as we go into the next part, we have to make sure of something first. Is the index here even or odd? Even. Did we get any results with odd powers?
Yes.
Which one?
9.
You have to put an absolute value around it. So if you have an even index and you get an odd result, you put an absolute value around it. Only in that case, okay? And we'll just keep reiterating it so you get the hang of it. Alright. Now here, you see how the index here is odd?
Correct.
So with that, when it's an odd index, you have nothing to worry about with the absolute value. You only have to worry about it when the index is even. So, we're going to now divide our powers by our index. What's 6 divided by 3?
2.
Any remainders?
No.
No. What's 3 divided by 3?
1.
1.
Good. No absolute values because our index was odd. So that's the final answer. Okay. What is the index here?
Even.
2.
Good. It's 2 and it's even. You're both correct. Alright. So, we know that in the end, if it's even, we're going to have to put absolute values around any results that have an odd power. That includes 1 as a power as well. So, how many times does 2 go into 3?
Once.
Once, with a remainder of
1.
1.
whatever the remainder is what stays in the inside. The power that stays on the inside. What is 5 divided by 2?
2 remainder 1.
2 with a remainder of 1. 1b has to stay behind. And what's 2 divided by 2? 1.
Exactly 1.
Exactly 1 with no remainder. So, what's up?
Would you put an absolute around both A and C?
Yes. So yeah, I was just about to say. So here, you have to put an absolute around A and C. Why about around those two?
Because they're odd.
Because they're odd. Now, if you prefer, you can group them together and put just one absolute value.
That is prettier.
Yeah, it makes it look a little, this just looks weird. It's like just lines, I don't know, it's just bizarre looking. So yeah, this is a little bit nicer. And we can do that because multiplication is what? Commutative. Waste of time. You guys wouldn't complain if somebody said they'd multiply your salary by an amount of money, would they? Would you?
But that has nothing to do with learning math, so.
Well, no, but multiplication is not pointless. Alright, this one here, so we're going to divide the powers. So what is 8 divided by 4?
2.
Good. How many times does 4 go into 13?
3 times with the remainder of 1.
3, good, with the remainder of 1. So that means 1y has to stay inside the radical. And what is 17 divided by 4?
4 with the remainder of 1.
Good, 4 with the remainder of 1. Perfect. So, absolute values, which one has to have one?
The Y.
Good. What do you think so far? Not bad?
Bad.
Well, if you say that about everything, then it just defeats the purpose, right? Gotta have some favorites. Okay.
Wait.
Alright, so now we're going to go ahead and mix together dealing with the numbers and the radicals, okay? And the variables, I mean. Okay. So, I want to mention that you can always rewrite this as the product of the numerical and the product of the variable. And I like to do that sometimes just to make things clear as I'm going. I kind of do each one separately and then I merge them together. You'll see. So, what kind of root is this? Is it a square root, a cube root, a fourth root?
Square root.
It's an implied square root. So what can I break up the 18 into?
2 and 9.
2 9.
2 and 9. 2 is prime. What about 9?
Break up into 2 threes.
Good. So since it's a square root, I'm looking for what size grouping?
2. So you would have the 3 on the outside and the 2 on the inside.
Very good. The 3 gets to pair up and leave. The 2 has to stay behind. Remember, if it pairs up, it only leaves as one of that item. Now, we still have to deal with the 8, the power of 8.
You divide that by 2.
Good. So what is 8 divided by 2?
4.
Good. Any remainders?
No.
No.
Which need to go on the outside.
Good. So now we have these two parts as our final answer. These are products. So here's the way you write the official final answer. The number, the coefficient is going to go first, then the variable that came outside, then the radical and what stayed inside of it. And as you can see here, we took an even root, but we don't have to worry about the absolute value rule. Why?
Because there is even power.
Good, there's no odd powers. Exactly. Any questions about that? All right. So here we have a second root, so this is even, right? What is 2 divided by 2?
1.
Good, 1. So this right here has a power of what on it? Technically.
1.
Is 1 odd?
Mm-hmm.
So we have to put in
Absolute value.
absolute value. So anybody in here who's banking on the SAT or the ACT either for college or for an equivalency score for like an exam, these are like super popular on those tests. Like they love these radical questions. When I do prep, we do so many of these. So this is like an important topic to focus on if you're working on toward any of those goals in those
What
tests.
exactly did you just do?
Here?
Yeah.
Well, this is the power. So 2 divided by 2 is 1.
Yes.
So then it's just 1 on this. It has a 1. And then since it's odd, you gotta put absolute value around it. It's like so simple that it's almost like confusing.
So, you just divided the 2, you took the 2 squared, and you took the radical out, you canceled them out, and then you're just left with that, but it's off.
Correct.
Okay, got it.
Exactly. Alright. So, anyone tell me what this one's gonna be?
4th root.
Good. So, x to the second, and then y to the third. We have any absolute values needed here?
Yes.
Where?
Why?
Good. Make sense? Okay. Let's go ahead and try a few more.
Sorry.
What is 6 divided by 3?
It'd be
2.
2, so it'd be a
Squared.
2, and then e to the power of 3, but then you put absolute around the 3.
No, you wouldn't.
Oh
You're
wait,
right.
no, it's an odd one.
Good.
It's an odd one.
So since this is odd, you don't have to. Good. Alright. This one here, we're taking a 4th root. So let's see what we can break this up into. Obviously, if you don't know where to start, you can always start with a 2 if it's an even number, right? So we have 486 divided by 2. That's 243. So I gotta circle this. Now 243 is divisible by maybe 3. We'll try that. Yep. So this breaks up into 3 and 81. And 81 breaks up into 9 and 9. And then 9 breaks up into 3s. So is everyone with me on how I got this?
Yes.
Okay. So everything circled, if you were to multiply all those numbers together, everything circled, those 6 numbers, that would give you the original number. So that's what we call the prime factorization, okay? You break everything down as much as you can. Now, what we're going to look for is groupings of what size here?
4.
Good. Since we have a 4th root, see how we have 4 3s right here?
Yeah.
So those 4 3s get to leave as 1, right? So 1 3 gets to leave.
But the other 3 gets left behind because it doesn't have 3 other 3s.
Good. So see these two right here? They actually get left behind inside the radical. So anything that leaves, anything that stays, if there's multiple things, they get multiplied back together. Okay? So that leaves me with the 4th root of 6, and then we'll deal with the number or the letter ones in a second. So I know we're not done yet, but this is like an intermediate step. So I like to do the numerical first, then I go back and do the variables, just so I'm not trying to do 2 things at once. But you work how you feel necessary to work. That's your choice. So now I've dealt with the number portion. I'm now going to work with the variables. How many times does 4 go into 9?
Twice, with a remainder of 1.
Good. Twice with a remainder of 1. So I have to leave an x behind. And how many times does 4 go into 12?
3 times.
Any remainder?
No.
And now we're almost done, but we took an even root, so we have to. Absolute value around what?
3.
The y. To the 3rd.
I have a question. Will we ever be doing like one where there's 2 groups of 4?
Yeah, that could happen.
What would you do with 2 groups of 4?
Good question. So say we had like a group of 3 and then a group of 2. You're going to take both the 3 and the 2 out, and when you do that, then they get multiplied together. So you'd be really taking out a 6.
Okay.
So anything that leaves, anything that stays, gets always multiplied. Good question. All right. So remember here what I told you, when it's negative, it's an odd root, so it's okay. But we're going to take that -1 out. It's just easier this way. Okay. So now, the good news is, if I look at my chart here, wait, just kidding, it's a perfect 4th root, but not a perfect 3rd root. So we're going to have to break it down. So I already know, once you get the hang of this, you're going to get used to breaking down the same numbers over and over again. And you're just going to like know what they break down into. So, 81 is the same as 4 3s, right?
Correct.
So, how many of these 3s get to leave?
Only 3 of them.
Only 3 of them get paired together, which means 1 3 actually gets to leave, right?
What?
So it's -1 that's already there, times the 3 that got to leave.
Yes. Oh, yeah.
But you're right, I see what you're saying. You were right in how you said it. It was just, I just want to make sure you understand. So then 1 3 has to stay behind. Does everyone understand why there's still 1 3 inside the radical?
Yes, because you could only pick 3 people.
Exactly.
So like, the power over the radical tells you how many people you can like invite outside, and there was only allowed to be invited 3.
Exactly, just like that. So this is going to simplify to -3, but now I have to deal with my variables. So here's the thing. Can 3 go into 2?
No.
That's true, but you can only divide this by this. So this has to stay inside, because I can't take any grouping of that out, as many as I need. What about the q to the 12? 4 times. And any remainder there?
No.
No. And no absolute because our index was odd.
Correct.
Make sense? Okay. The last ones are easy. I think they're all pretty easy. Yeah, they are. All right.
Wait, can you just go back to this?
Yeah, sure. No problem.
Thank you.
You're welcome. Okay. So, good news about this one. If you look at your chart, what do you notice the perfect cube root of 64 is?
8.
That's the perfect square root.
Oh, cube.
4.
4. So what do you think the perfect cube root of negative 64 is?
Negative 4.
Negative 4. Remember, it's okay. Negatives are okay when the index is odd. And then, what is 10 divided by 3?
Oh, 9 with the remainder of 1.
Good. And then the y is going to become y to the?
7.
Good. No remainders on that. That's it. Uh, 4 divided by 4 is? So w to the 1. Yeah, go ahead. And then v to the 17th, that's going to become?
4 to the 6.
Good. So it's going to become 16 because of the 4 because of the 16th. And then what has to stay behind? How many of these?
1.
Just 1, because the remainder is 1. You're all familiar with the remainder theorem, how that works? Okay. Now, do I have to put any absolute values here?
W.
Good. Eight divided by 4?
2.
There we go. Okay. So that's the answer to this one, but they love to be tricky on standardized tests. So what they could have done is, say you get this answer, but none of them are the answer choices. They could have taken these and done what with the two of them? Multiplied them with FOIL. So the answer could have been written like this. You know what I'm saying? And that would have been the same answer. But just be aware of those kind of things, okay? Knowing all your math skills. Alright, so the homework is only 1 page today. Lucky you. You have a little bit of time in class for it.